So now we're going to discuss the Newton method, or the Newton-Raphson method. Okay, so first we're going to suppose that f is an element of the set of all functions that have two continuous derivatives on the closed interval ab. We're also going to let p0 be an element of the closed interval ab, and we're going to approximate p such that f prime of p0 is not equal to 0, and the absolute value of p minus p0 is very small. Next, we're going to consider the Taylor polynomial for f of x expanded about p0 and evaluated at x equals p. Okay, so the nth degree Taylor polynomial is given by the expression p sub n of x is equal to the sum from k equals 0 to n, the kth derivative of f evaluated at x naught over k factorial times x minus x naught to the k. Okay, and so that means that when n equals 1, we have p sub 1 of x equals sum from k equals 0 to n equals 1 that's equal to okay, and then our remainder r sub n of x is equal to the n plus 1 derivative of f. Then we have c of x, which is our truncation error, over n plus 1 factorial. And so r1 x equals okay. So since f of x equals the nth degree Taylor polynomial plus the remainder, we can say that f of x equals f f naught, sorry, the zeroth derivative of f plus first derivative And since we're considering the Taylor polynomial for f of x expanded about p naught and evaluated at x equals p, we can say that f of p is equal to zeroth derivative of p naught plus first derivative p naught p minus p naught plus second derivative c of p over 2 factorial p minus p naught squared. We also know that because of the root, f of p is equal to 0. And that if the absolute value of p minus p naught is small, then of course p minus p naught squared is roughly 0. Okay, and so taking that into consideration and plugging it back into that Taylor expansion, we can say that p is approximately p naught minus f p naught divided by f prime p naught. That's going to be defined as p1. Okay, so we're going to go ahead and start with an initial approximation p naught and generate some sequence. The sequence is going to be Pn equals 0 to infinity via the formula P sub n, which is equal to P n minus 1 minus f of Pn minus 1 divided by f prime of Pn minus 1. And this is going to be for all n greater than or equal to 1. So we'll go ahead and program that up in VBA.
Okay, so we're going to use VBA to write a subroutine. So we say option explicit, and we can say sub Newton-Raphson. And then we're going to dim the variables. And we know that I and n are integers. And we're going to say that the error, the tolerance, P naught, and those are going to be double precision. And then we're going to input, and the input parameters are the n, which is the value of the iteration, the maximum value of the iteration. So I equals 0, 1, 2, 3, blah, 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 all the way to n. So we're going to say n is some integer 100. We want our tolerance to be some small number and we want p naught to be some number as well, and we'll say p naught equals 0 in this case. So we want the error to be less than the tolerance. So if you're comfortable with it being 0.001, then that's fine. If that error is good enough for you, if you need a better, if you need more precision in your answer than that, then you can change the tolerance as an input parameter. And we're going to output what we want from this subroutine. And we're going to come back to this later. Okay. So in order to use this numerical method, we need to have a function that we're studying. And so as a demonstration, we could say the e to the minus x minus x. And for Newton's method, we need to know f prime, or the derivative of f of x, in order to iterate. So we'll say take the derivative of this function. Okay, so we've got this function f, we've got the derivative of f, and we need to also write a function Newton-Raphson, which evaluates the iteration. And so we can go ahead and put our input parameters from the subroutine into that function. And we are going to dim the variable that gets updated by this function. So this function nr is going to update p until we find the root of f of x. Okay, so we're going to initialize our iteration with I equals 0 and with p equals to p naught. So that value of p naught is coming from here. Doesn't have to be 0, but we're taking p naught to be 0 in this example. And then after we've initialized our iteration, we're going to perform the iteration. Do, and then p old equals p. P equals p minus f of p divided by df of p. Then I equals I plus 1. from Newton's formula, we can update p and then iterate. But we also need to describe the error between this iteration and the exact solution. And we also need some Okay, so if the error is good enough for us, if it's less than the tolerance that we specified up here, or if the iteration exceeds the maximum number of iterations that we put here, then we can exit the loop and output the result of the function, which is the p. Okay, so now let's come back to the output that we want from this subroutine Newton-Raphson. So we can message box and then we can actually message box this function nr. We can also message box which is coming from here. Okay, so it looks like we can go ahead and run this subroutine. The root of f of x is 0.567, etc. And the error of the estimate is 2 times 10 to the minus 5. So we have used VBA to write a code for the, or a subroutine for the Newton-Raphson method, which gives us the root of a function as an open method versus a bracketing method. All right, thank you.